Hello, my name is Chance Jones, and I have been working with Dr. Krishna Shah in the Department of Mechanical Engineering, and today I'll be presenting my research on characterizing battery performance in hybrid electric aircraft. To start, the main motivation for this project was found during literature review. It was quickly noticed that there was a large focus in the current research in hybrid electric aircraft on battery efficiency, and there was a large gap in the research when it came to battery life and sustainability. This led to the formation of one of the main future goals of this project, being to find the optimal degree of hybridization per flight phase, those phases being climb, cruise, and descent. For a quick background, hybrid vehicles are vehicles with both a fuel engine and an electric motor as power sources. So the degree of hybridization would be the percent of power coming from one of the sources, in this case the electric component. For example, a 60% hybridization would be 60% of the total power coming from the electric component. This project has a focus on sustainability and balance, as well as maximizing efficiency while minimizing waste. Going into this project, I was provided a model for battery performance of electric aircraft. This model simulates battery dynamics as well as flight dynamics. The first goal was to adapt this model to work for hybrid aircraft and not just electric aircraft. This model was built around the Airbus eFan 2.0 tech demonstrator and its specs. This model outputs power in kilowatts and the corresponding time, and it simulates a generalized flight path with climb, cruise, and descent. This output can be used with a type of testing called cycling. What cycling is it repeatedly charges and discharges a battery cell in order to simulate some sort of situation, in this case the flight path. So the model's outputted power and time data can be used as a sort of map for the cycling software to use to simulate the stress and that the battery would go through in a flight without having to actually leave the lab or have an actual electric aircraft. Now, the three main phases are, as stated before, climb, cruise, and descent. And when adapting the model, I implemented three different hybridization variables, being mu-c for climb, mu-r for cruise, and mu-d for descent. The reason I implemented three variables as opposed to just one hybridization factor was to allow for more variation when it comes to testing. As stated prior, the model outputs power in kilowatts of the entire system. For the cycling software, we're going to be cycling one cell, and it needs it in watts. So the power needs to be converted with a simple equation as seen here. The power of the system is multiplied by 1,000 to get from kilowatts to watts, and then divided by 60 for the number of cells in parallel, and then divided by 12 for the number of cells in series, and then divided by 2 for the number of packs. Per every point of power data, it is multiplied by mu-n, where n represents the phase of flight that it's currently in, and these could be the same or different depending on the test case being used. Since there are three different hybridization factor variables, this allows for varied power split test cases. As a baseline, we started with 50-50-50, or a total hybridization of 50%. Since we are trying to see which hybridization power split results in the best battery sustainability, it's necessary that we apply the constraint of conserving energy and having the same total energy per case. If we do not have this constraint, the best power split test case for battery life is going to be zeros all across the board. If you don't use the battery, it's going to live for a long time. So that's why we have to conserve energy. Energy can be easily calculated since it is power multiplied by time, or the integral of power as a function of time with respect to time. The energy for each of the phases was calculated and summed together to get the total energy. And on the right here, you can see an example of the outputted data in watts and the corresponding time for 3 different phases. Here we have, using a simple approach, the 50-50-50 baseline test case and its corresponding energy, and some rough approximates with other cases that can be used in the future, being 95-20-95, 65-40-65, 35-60-35, 80-30-80, 5-85, and 20-70-20. Now, the energies here are not exactly the same, but they can provide as a nice start for going forward when we have more accurate methods, which should be coming up very soon. On the right here, we have a graph representing the power and time data, and you can clearly see the different flight phases. Now, for future work, the first step is to find exact energy efficient power splits and test cases. As before, the test cases were close, but they didn't have the exact same energies, but that is going to be coming up soon, as well as tied different variations, such as before there was a constraint placed of the hybridization of the climb and descent phases being the exact same, but that is not required. It was just for ease of initial testing. The cycling also needs to begin shortly, but due to a limited number of cables available in the lab, that will come in the coming weeks, and that cycling will probably take a couple months. The goal is to find which hybridization is best for battery life, as well as another future thing could be to find how does engine weight scale with power output. And the main goal in the long run is to turn this into an optimization problem. Once we have an engine model, we can find, we can add a constraint of using between like 20 to 40% total hybridization. We could see which hybridization level has the best efficiency as well as the best sustainability. Are there any questions?
So one thing I noticed was with the power splitting, you picked hybridizations that had the same for the climb and the descent. Mm-hmm. Can you explain a little bit more about why you chose to do that and how you chose the power splits in general?
So I chose to do that just for ease of calculation, to get some initial cases, some initial numbers. In a thinking logically, the most draining part of the whole process is going to be the climb phase. The descent is not going to necessarily need that much power, so we're probably going to have the most hybridization being on the climb phase, and descent might not need much at all. But this was just to make it easy to get some initial cases, and these were chosen. The first one was found using just a little guesswork, and then a pattern was quickly formed, but an equation can be used as well.
Assuming you knew the hybridization in each stage of flight, could you use this model to determine what the most efficient or the longest lasting battery type would be? Like, could you use it to compare different batteries with slightly different wear curves?
I think that should be fine, because we're trying to build like a framework that we can apply to not just like one aircraft, but multiple. So we could also do the same with different batteries. So the same way in the model, we can just change the specs of the aircraft to adapt it towards a different plane. I believe we could just test it on different batteries and see with the same conditions which ones have better results.
I think around slide 4, you're talking about testing of the cell. You're talking about when you're cycling, or maybe it's 3, when you're only when you're testing the cells, you're doing it one at a time. Can you explain why that's required when you're doing the cycling?
So the cycling, which hasn't been gotten to yet, but well, hopefully soon, it's one at a time just due to mainly right now a resource limitation due to other projects going on at the same time that also need cycling done. But also, we are only testing one cell at a time because we don't have battery packs. They're very large, these packs, as you can see, 60 in series, I think, 12 in parallel, maybe the other way around. There's a lot of cells going on, and it's a lot easier in a lab condition to just test one cell at a time than the entire battery pack.
Yeah, I had one last question for you. I don't know if you mentioned this in your presentation, but I know that there's a lot of talk about sustainable air fuels, right, in the market. And I was wondering, when you talk about hybridization, do you ever foresee a situation where you could be using electric batteries along with sustainable air fuels, or is this purely focused on conventional sources of fuel right now?
I think absolutely. I think that'd be a great place to take it. There should be no reason, again, once this framework is set in place down the line, there should be no reason to just limit whatever engine model we use. Once we get to a point where we have that sort of like optimization methodology set up, we could produce maybe a new engine model for a more environmentally conscious fuel or a sustainable fuel source, and incorporate that in addition towards our efficient hybridization power splits. Thank you for, this has been day 2 of RRS Live. Thank you for tuning in, and please come back tomorrow.